So a moment ago we solved the question that these three vectors are linearly dependent, right? Yeah. But here's another way to see it. If you form a matrix using those three vectors, so I had the three vectors as 0, 1, 0, 1, negative 1, 3, 2, and 1, 3, 4. And by the way, this only works for a square matrix. So if you're given two vectors and asked, the question is to figure out if it's linearly independent or not, you can't use this. But at least because we have three vectors in dimension 3, and we're being asked whether this is linearly independent or not, here's a second way to figure that out. See, we learned that for determinants, you have this elementary operations that leave the determinants fixed. Do you remember that, right? You can take any, well, we did the row operations, but the column operations are the same. You can take any multiple of a column and add it to another one, and it does not change the value of the determinant. So if we do that, if we take, say, if we take negative 2 of this and add it to the third one, here's what we get. We get 1, 0, 1, negative 1, 3, 2. Negative 2 times 1 is negative 2, so you're basically subtracting 2 here, subtracting 2 here, leaving this unchanged. Oh, but wait. Immediately after that, you see that if you subtract this over to the third column, times negative 1 and add it to the third column, then what do you get in the third column? You get 0, 0, 0, right? So what does that say? It says that this determinant must be 0, because if you do column expansion with the last row and last column, it will be 0, right? So that tells us that if you have n number of vectors in n-dimensional space, one quick way to figure out whether the system is linearly independent or not is just simply by taking the determinant of the matrix formed by taking those column vectors, putting them together as a square matrix. That's nice, right? It makes things easy.